There is a machine rolling around northwest China right now that should not exist on wheels. It weighs so much that a single one of its moving parts tips the scale at 32 tons. One small part. Its main arm stretches taller than a 60-story skyscraper. When it lifts something heavy, the counterweight holding it in balance weighs more than the entire Statue of Liberty, base and all. And the truly wild part? It drives on public roads. It rolls past regular cars, past gas stations, through everyday traffic, just like a really, really, really large truck. This is the Zoomlion ZAT8000H. It is a crane that rolls on rubber tires. As of right now, it is the largest, heaviest, most powerful wheeled crane ever built on planet Earth. But here is the thing about big numbers. 4,000 tons of lifting capacity, 186 meters of reach, 28 support vehicles in its convoy. Those numbers sound impressive, but they do not actually tell you anything. Not really. So, let us make them real. The best city cranes you see poking above buildings at construction sites can lift around 900 tons. That is already a wild amount of weight. Really the equivalent of 600 cars. And those big city cranes are considered the serious machines of the construction world. Engineers spend years designing them, companies spend millions buying them, and they are genuinely impressive. Now take that crane and multiply it by 4.5. That is Zoomlion's new monster. It is not a slight improvement over what came before. It is not a modest upgrade. It is a completely different category of machine. Going from a regular crane to this one is like going from a bicycle to a fighter jet and then strapping rocket boosters to the fighter jet. The gap between the two is so large that comparing them almost feels unfair. So where did this thing come from and why did it need to exist? The answer starts in a factory in Changsha, China. Zoomlion is a Chinese company based in Hunan province, and they have been building cranes for decades. Over the years, they kept building bigger ones. First a 2,000-ton crane, then a 2,400-ton crane. Then, they walked out of their factory with a 4,000-ton machine and told the world, "This is the largest all-terrain crane we have ever made, and it is the largest one that has ever existed on wheels anywhere on Earth." The construction world stopped and stared. Because this was not just a bigger crane, this was a machine built for a very specific, agonizing problem that nobody had solved yet. A problem sitting thousands of kilometers away in one of the emptiest, windiest, most unforgiving places on the entire planet. And to understand that problem, you need to understand what is happening out in the Gobi Desert right now. Because what China is building out there is honestly just as mind-blowing as the crane itself. The Gobi Desert in northwest China is not the kind of desert you see in movies. There are no soft, golden sand dunes or gentle breezes here. This is a hard, dry, wind-blasted stretch of gravel and rock that goes on for what feels like forever. Temperatures can swing from scorching heat during the day to bone-chilling cold at night. There are almost no people out there, and very few roads were ever designed for heavy machinery. And the wind is relentless. That wind is exactly why China sent an army of engineers out there. China needs energy, a lot of it. For decades, most of that energy came from burning coal. But coal is dirty, coal is expensive, and the logistics of moving it are a constant headache. To change that, China launched one of the most aggressive infrastructure shifts in human history, going out into the areas with the strongest, most reliable wind and building massive, sweeping wind farms. The Gobi and the nearby deserts of Xinjiang are perfect for this. The wind out there blows hard and steady nearly all year round. Here is the part that most people do not realize about wind turbines, though. They keep getting bigger. And size matters for a very specific physical reason. A taller turbine with longer blades catches higher, more consistent wind currents. More wind means exponentially more power. More power means more homes lit up, more factories running, and more electric vehicles charged. Every extra meter of height is worth serious money in electricity output. Back in the early days of wind power, turbines stood maybe 50 to 60 meters tall. Their blades were around 25 meters long. Today, the turbines being installed in China's desert regions stand over 170 meters tall. That is taller than most skyscrapers in any city you have ever visited. And their blades stretch over 100 meters from root to tip. The turbine at the center of this whole story is a 6.25 megawatt machine. At full power, it can produce enough electricity in a single hour to power hundreds of homes. Just one turbine. And out in the Gobi, the plan is not to build one. It is to build thousands of them. Stretch your eyes across the horizon in Xinjiang right now, and you will see hundreds of those white towers already spinning against the gray sky. But here is the catch that nobody talks about. The taller a turbine gets, the harder it becomes to build. Think through what it actually means. To build a turbine that stands 170 meters tall, you have to carry a steel tower in massive, heavy sections to the middle of a barren desert and stack it upright, piece by piece, like giant Lego blocks. Then, at the very top of that tower, you have to place a huge metal box called a nacelle. That nacelle holds all the working parts: the gearbox that controls the spinning, the generator that makes the electricity, and the control systems that monitor everything. This particular nacelle weighs over 150 tons. You have to lift that 150-ton house-sized box 170 meters into the air and bolt it precisely onto the top of the tower. And then you have to attach 3 blades, each one longer than an American football field, to that nacelle up in the sky, at the height of a 60-story building. Before this new machine was built, no wheeled crane in the world could do this job. Regular cranes that work in cities can get up pretty high, but not anywhere close to 170 meters, with a 150-ton load hanging off the edge. The giant cranes that sit on crawler tracks, the kind that look like tanks and are used in the heaviest industrial shipyard work, can lift more, but they move at a literal snail's pace. They destroy the ground beneath them, and getting one out to a remote desert site means a months-long nightmare of completely dismantling the machine, loading it onto dozens of specialized trains and flatbeds, and rebuilding it slowly on site. What the Gobi Desert needed was a paradox: a crane that could reach 186 meters into the sky, lift hundreds of tons at that height, yet travel on public roads without special wide-load permits, set up quickly, and handle rough desert terrain without getting stuck. That crane did not exist, so Zoomlion built it. And then came the part that might actually be harder than building the crane itself. Getting it there, you have just built the largest wheeled crane on planet Earth. And now you need to drive it across 2,000 kilometers of China to reach a construction site deep in the Gobi Desert. Obviously, you cannot just drive it in one piece. That would be physically impossible. Instead, it gets broken down into hundreds of separate pieces, loaded onto heavy transport vehicles, and shipped across the country as a massive convoy. The full convoy consists of 28 support vehicles moving together with the main carrier. When you see that line of trucks and flatbeds rolling down a highway, it does not look like a construction delivery. It looks like a slow-moving steel city. But here is the engineering detail that stops people cold when they hear it. The crane was designed specifically so that its widest single piece is only about 3 meters across. That is just barely narrow enough to travel on standard highways without needing permanent police escorts or blocking off multiple lanes of traffic. For a machine of this scale, that is almost miraculous engineering. Yet, even folded down, the parts themselves are staggering. The slewing platform, the big circular base that lets the crane rotate 360 degrees, weighs 65 tons on its own. That is the weight of about 12 full-grown African elephants cast into a single piece of steel. The 2 base sections of the main boom weigh 66 tons each. The hydraulic cylinders that push and pull the crane's massive arms into position weigh 32 tons per cylinder. To carry all this without destroying the country's infrastructure, the main crane chassis sits on 10 axles. 10 axles, all working together, sharing the enormous weight of the machine so precisely that no single tire presses down hard enough to crack the asphalt. Covering those 2,000 kilometers from Changsha to the northwest means navigating mountain passes, tight highway tolls, and varying road conditions. But when the convoy finally arrived at the desert site, everyone took a breath, because now came the part that corporate blueprints could not fully prepare them for. They had to put it all back together in the middle of a wasteland, far from any factory support base, while the desert wind was already starting to howl. Assembly of this crane is a multi-day operation that requires smaller support cranes just to lift the main crane's own pieces into position. Think about that. The machine is so big that you need a fleet of regular cranes just to build it. First, they connected the 65-ton slewing platform, aligning 2 perfectly round steel bases on top of each other while the wind pushed against the metal. Then came the outriggers, those thick, extendable legs that spread out from the sides to keep the crane from tipping. On the feet of each outrigger, workers placed massive, wide, flat pads. These pads are critical. Without them, the tremendous weight of the crane would concentrate into small points. and the machine would slowly press itself straight down into the desert floor, swallowing its own wheels. Next, the main lifting boom was assembled from 7 separate sections. Normally, connecting crane sections involves workers swinging massive sledgehammers in the heat to force heavy steel pins into place. This machine, however, uses automated hydraulic cylinders. The pieces line up, the system pressurizes, and the massive pins slide into place cleanly and quietly once the boom was up. They deployed the superlift wings, 2 enormous steel arms that extend out from behind the crane like the wings of a giant bird. These wings hold the counterweight that keeps the crane balanced. For this specific 6.25 megawatt turbine installation, the team loaded 260 tons of counterweight onto those wings. And the wildest part? 260 tons was not even close to its full capacity. The crane was barely breaking a sweat. With the superlift wings deployed and the boom fully extended, the crane stretched to its final working height. It stood on the desert floor, fully assembled, looking less like construction equipment and more like a weapon from a science fiction film. It was finally ready for the lift. The tower was up, standing 170 meters tall. The 150-ton nacelle was rigged to the crane's cables. To prevent it from becoming a giant catastrophic pendulum in the desert air, 4 separate teams of workers held long rope lines attached to each corner of the nacelle, walking with it as it slowly left the ground. Manual tension fighting the wind. Step by step, the crane hoisted the massive powerhouse higher and higher, until it successfully settled onto the top of the tower. The bolts were secured. The team on the ground let out a breath they had been holding for hours, but as the sun began to set, the real nightmare began. Because the nacelle was just the center, now they had to lift the blades. Each blade is 108 meters of lightweight composite material. But lightweight is a relative term when a single blade still weighs 30 tons and catches the wind like a massive ship sail. Lifting a 108-meter wing to the height of a skyscraper in a desert known for sudden violent gales is an equation where a single mistake means total destruction. The team laid the first blade on the ground and checked their instruments. The wind gauges were spiking. The lift was impossible, so they waited. They waited through the evening. The wind kept blowing. They settled in for the night, sitting on the cold desert floor, watching the flags, watching the sky, knowing that every hour of delay cost fortunes. Then, just before dawn, the wind stopped. The air went completely. Eerily calm. That brief window of absolute stillness that deserts sometimes experience right before sunrise, the radio crackled to life. The call went out, and everyone moved. The crane lines tightened, and the first 30-ton blades slowly lifted into the dark sky. The rope teams strained, the operators stared at their monitors, and the massive wing rose higher and higher against the pre-dawn horizon. And right as the sun began to crack open the sky, lighting up the desert, the blade finally reached the top and locked into place. It was a triumph of engineering. But as the engineers celebrated on the ground, looking up at the completed, towering structure, someone noticed something on the horizon, a change in the weather patterns that the instruments had completely failed to predict, moving rapidly toward the unfinished wind farm. And that is where the story stops making sense. To understand why the engineers in the Gobi Desert suddenly went cold, you have to look past the sheer size of the ZD-2400H and look at the physics of what it is actually doing. Because on paper, a crane this size should not be able to stand up, let alone lift a 150-ton metal box to the height of a skyscraper. The secret to why this machine works lies in a concept that every structural engineer obsesses over: structural leverage. When a crane lifts a heavy load at the end of its long boom arm, it is essentially acting as a giant seesaw, the point where the crane body connects to the ground. The outriggers is the pivot point. The heavy load at the front pulls down, trying to tip the entire machine forward. To stop that from happening, you need an equal or greater force pulling down on the back. That is the counterweight. But as a turbine gets taller, the problem does not just scale up linearly, it multiplies. The higher you lift a load, the further away from the crane's center of gravity it usually has to sit, simply due to the angle of the boom. In physics, torque is calculated by multiplying the weight of the object by its distance from the pivot point. If you double the height and distance, you quadruple the tipping force. Lift a 150-ton nacelle at ground level, and it feels like 150 tons to the machine. Lift that same nacelle 170 meters into the air at a steep angle, and the leverage makes it feel like thousands of tons are trying to rip the crane's base right out of the dirt. to fight this brutal physics equation. Zoomlian's engineers could not just stack more concrete blocks on the back of the machine. If they did, the crane would become so heavy it would crush its own internal components before it even picked up the blade. Instead, they invented a system called the variable superlift. Think of the superlift as a pair of massive, automated steel wings that extend out from the back of the crane's rotating upper body. These are not static metal beams. They are dynamic structures controlled by massive hydraulic cylinders. When the crane is preparing for a normal lift, the wings stay tucked close to the body. But when the crane needs to reach up to that 170-meter threshold, the hydraulic systems push these wings outward and backward, extending the distance of the counterweight from the center of the machine. By moving the 260 tons of counterweight further back, they dramatically increase its leverage without adding a single extra kilogram of physical mass. It is the exact same principle as moving further down a seesaw to lift a heavier person on the other side. The crane adjusts its own shape in real time based on how high it is reaching and how much the load weighs. But increasing the counterweight leverage introduces a terrifying new vulnerability. What happens when the crane is holding that massive 150-ton nacelle high in the sky, and suddenly it has to set it down? Or worse, what happens if the wind shifts or a cable tension changes and the load at the front is suddenly reduced? If the front of the crane suddenly becomes lighter, that massive extended counterweight at the back is no longer balancing anything. It becomes the dominant force. The leverage flips instantly. Instead of tipping forward, the entire multi-thousand-ton machine will violently tip over backward, crushing its own support vehicles and collapsing into the desert floor. To prevent this catastrophic backward tipping, the ZAT-2400H uses a nonlinear computer control system tied to hundreds of high-precision pressure sensors embedded in the outriggers and the boom. The system monitors the exact weight distribution across all four corners of the machine milliseconds at a time. If a sensor detects that the pressure on the front outriggers is dropping too fast, meaning the machine is starting to lean backward, the hydraulic cylinders on the superlift wings instantly pull the counterweight closer to the body, reducing its leverage and restoring balance before a human operator could even realize anything was wrong. Then there is the boom arm itself. To reach 186 meters, the boom cannot just be a solid piece of steel. It would be far too heavy to lift itself. Instead, it is made of 7 telescoping sections engineered from ultra-high-strength, low-alloy steel. This material is designed to bend. When you look at the crane from the side during a heavy lift, the main arm actually curves noticeably like a giant fishing rod. This flexibility is intentional. If the steel were completely rigid, the intense, concentrated forces of the desert wind hitting a 108-meter blade would snap the boom like a dry twig. By allowing the metal to flex, the structure absorbs and distributes the kinetic energy of the wind across the entire length of the arm down to the chassis. But telescoping 7 massive sections of steel together creates another massive engineering hurdle: the joints. In older heavy cranes, each telescoping section had to be manually locked into the next, using massive steel pins that workers hammered in by hand. On a machine of this scale, that process would take days and put workers at extreme risk at dangerous heights. Zoomlian solved this with an internal single-cylinder pinning mechanism. Inside the hollow center of the boom runs a single, incredibly powerful hydraulic cylinder that moves independently. It travels up the inside of the arm, grabs a specific section, pushes it out to the exact millimeter required, and then hydraulically drives heavy steel pins outward to lock that section into the outer shell. It then releases, travels back down, grabs the next section, and repeats the process automatically. This internal mechanism allows the entire 186-meter structure to erect itself cleanly, with pinpoint accuracy, completely controlled from a digital touchscreen inside the operator's cabin. But all of this incredible technology, the variable wings, the balancing computers, the self-assembling boom, relies on one single, unyielding foundation. It relies on the ground beneath it holding perfectly still. And that is exactly why the sudden change in the desert weather patterns sent a wave of anxiety through the engineering team, because as the morning sun began to heat the Gobi Desert, the air temperature rose rapidly, creating an intense, localized low-pressure zone. The calm window of air that had allowed them to install the first 2 blades vanished in an instant. A sudden violent thermal updraft slammed into the side of the crane, right as the third and final 108-meter blade was being lifted into position. The wind speed indicators inside the cabin did not just rise, they went off the charts. The 30-ton blade hanging on the cables caught the thermal blast and began to twist violently, acting like a giant uncontrolled wing trying to fly. The massive torque forces traveled down the 186-meter flexing steel boom and slammed directly into the rotating base of the crane. Suddenly, the balancing computers began screaming. The pressure sensors on the eastern outriggers registered a terrifying drop. The sand beneath one of the massive support pads, dried out and loosened by the sudden shift in wind currents, began to shift. The world's largest wheeled crane, with a 30-ton blade suspended over 100 meters above the earth, was losing its footing. When the ground beneath a multi-thousand-ton machine starts to give way, you are not just looking at an engineering crisis. You are looking at the exact physical boundary where human ambition collisions with the laws of nature. The operator inside the cabin did what only elite heavy machinery pilots are trained to do: nothing hasty. A sudden movement of the controls would have introduced a massive dynamic load, a jolt of kinetic energy that would have snapped the flexing steel boom or flipped the chassis instantly. Instead, the automated systems caught the shift. The variable superlift wings adjusted in milliseconds, pulling the 260-ton counterweight inward to recenter the gravity, while the operator slowly ground the blade's rotation to a halt against the wind. The ground held. The sand compressed. The machine stabilized. But that terrifying moment reveals the real reason this crane matters to the rest of the world. It is the physical manifestation of a massive, quiet geopolitical arms race that most people completely miss. This is not just about one company building a giant machine to show off at trade shows. This is about a critical bottleneck in the global transition to renewable energy. To understand how we got here, you have to look at the history of heavy lifting. For decades, the undisputed kings of the crane world were European companies, specifically German engineering giants like Liebherr and Demag. If you needed to build a nuclear power plant, a massive oil refinery, or a massive bridge anywhere on Earth, you bought or rented German equipment. They owned the patents, they mastered the high-strength metallurgy, and they set the global standard for safety and precision. China, meanwhile, was decades behind. In the 1980s and 1990s, Chinese construction sites relied on imported, often second-hand foreign machinery. If a critical component broke on a major project, engineers had to wait weeks for spare parts to be shipped from Europe, completely halting development. For a country planning the fastest, largest urban migration and infrastructure buildup in human history, that dependency was a massive strategic vulnerability. So, the Chinese government enacted a deliberate long-term policy to build its own domestic heavy machinery ecosystem. Zoomlion, XCMG, and SANY were born out of state-backed research institutes and local manufacturing hubs. At first, they did what many late-coming manufacturing sectors do. They reverse-engineered foreign designs, built cheaper versions, and competed strictly on price. But over the last 15 years, that dynamic underwent a massive radical shift. The apprentice didn't just learn from the master. The apprentice outgrew the master's entire workshop. The catalyst for this shift was not a desire to build the biggest sandbox toys. It was the specific, aggressive topography of China's own geography. When Europe began building massive wind energy networks, they focused heavily on offshore wind farms in the North Sea, where ships and specialized barges could carry massive components easily. But China's energy blueprint required tapping into the vast, inland interior. The high-altitude plateaus of Inner Mongolia, the mountainous ridges of Yunnan, and the remote deserts of Xinjiang. You cannot bring a massive, slow-moving crawler crane that requires a 50-truck convoy and 3 weeks of assembly up a narrow, winding mountain road with a 15-degree incline. The logistics alone would destroy the economic viability of the wind farm before it produced a single kilowatt of power. The market demanded a machine that could drive itself up a mountain, set up in 24 hours, perform a single massive lift at skyscraper heights, pack itself up, and drive to the next ridge the very next day. By forcing their domestic manufacturers to solve this hyper-specific, regional logistical nightmare, China accidentally created a global monopoly on high-mobility megalifting. European manufacturers focused on different market demands did not build wheeled cranes of this scale. Zoomlion and its domestic competitors filled the vacuum, pushing past 2,000 tons, then 3,000 tons. and now touching the 4,000-ton threshold on rubber tires. This brings us to the massive, overarching trend that this crane is driving: the scaling laws of green energy. Right now, energy experts talk about a concept called the levelized cost of energy, LCOE. It is the lifetime cost of building and operating an energy plant divided by the total amount of electricity it generates. For wind power to completely kill off coal and natural gas without government subsidies, its LCOE has to be lower than fossil fuels. And the fastest way to drop that cost is to build taller towers. When you double the height of a wind turbine tower, you don't just double the wind output. You get access to higher, smoother laminar airflows that are completely undisturbed by the friction of the Earth's surface. The wind blows faster and more consistently up there. Because the energy output of wind is proportional to the cube of the wind speed, a slight increase in altitude yields a massive exponential spike in power generation. But as we established, the rest of the world's crane infrastructure is stuck under a physical ceiling. In the United States and Europe, hundreds of planned onshore wind projects are currently stalled or facing massive cost overruns because project managers cannot find cranes capable of lifting the newest generation of 6 to 8 megawatt turbine components to these extreme heights. The technology of the wind turbines has evolved faster than the machines required to build them, except in China. By building the ZAS TWI-400H and its immediate competitors, China has effectively removed the physical ceiling on its green energy deployment. They can design 10 megawatt onshore turbines because they know they have the rolling logistics network ready to install them in a matter of days anywhere within their borders. It is a complete closed-loop industrial ecosystem. The state demands the energy. The engineering firms design the massive turbines. The machinery companies build the impossible cranes to erect them. And the resulting ultra-cheap electricity flows back into the factories to build more cranes. This loop is moving at a pace that genuinely terrifies Western energy analysts. In 2024 alone, China installed more wind capacity than the rest of the world combined did over multiple years. They are building the equivalent of several massive nuclear power plants worth of generation every single month out in the desert, entirely out of sight of the global public, which brings us back to the completed massive 170-meter tower standing in the quiet of the Gobi Desert. The third blade was eventually secured. The crane lowered its massive telescoping arm, folded its variable wings back into its chassis, and rolled off toward the next coordinate on its GPS map. It left behind a monument of modern engineering, a spinning white giant, turning moving air into economic dominance. But as you watch those blades sweep an area larger than multiple football fields with every single rotation, it forces you to confront a deeply unsettling question about the future of global technology. Because this massive project was not accomplished by a single breakthrough or a stroke of luck. It was the result of a decades-long, highly coordinated industrial strategy that combined metallurgy, digital balancing physics, and raw logistical muscle to solve a problem the rest of the world didn't even realize was a trap. And that leaves the rest of the world facing a stark, historical reality that goes far beyond renewable energy. The real trap of looking at a machine like the Z8 8000H is assuming that the story ends once the crane drives away. It is easy to focus entirely on the spectacle of the lift, the high-stakes drama of a 30-ton blade hanging in a sudden desert gale, the sheer visceral thrill of watching a vehicle with 10 axles navigate a public highway alongside regular commuter cars. We love to see the moment where human grit beats the elements. But if you only look at the moment of installation, you are missing the entire point of why this machine was allowed to exist in the first place. Because that single, towering wind turbine out in the middle of the Gobi Desert is not an isolated victory. It is one single cell in a massive, interconnected living organism that is fundamentally altering how humanity generates and distributes power. Think back to the hook that started this whole journey. A machine rolling around on rubber tires that weighs so much and reaches so high that, according to standard engineering textbooks from 20 years ago, it simply should not exist on wheels. The conventional wisdom said that if you wanted to lift 150 tons up to 170 meters, you had to accept the slow, agonizing reality of a tracked crawler crane. You had to accept the weeks of downtime, the massive financial bleeding of logistics, and the permanent destruction of the terrain. The Zomlian's engineers looked at that absolute law of construction physics and realized it was actually just a design limitation waiting to be broken. By fusing high-strength metallurgy with dynamic hydraulic wings and real-time computer balancing systems, they didn't just build a larger tool, they shifted the entire boundary of what is logistically possible. And that shift changes the math on a global scale. When you look at the landscape of international infrastructure right now, the biggest bottleneck to saving the planet from carbon emissions is no longer the efficiency of solar panels or the aerodynamic design of wind turbine blades. We already know how to capture the energy. The bottleneck is the sheer, brutal physical reality of deployment. It is the unglamorous, exhausting work of moving massive pieces of steel and composite material from a factory floor to a remote ridgeline, and doing it thousands of times over without going bankrupt. By creating a fleet of these high-mobility megacranes, China has essentially industrialized the deployment process itself. They have turned what used to be a highly specialized, months-long engineering project into a routine, rapid assembly line that moves across deserts and mountains like clockwork, while the rest of the world debates the policy, the financing, and the regulatory permits required to approve a single new green energy corridor. These 28-vehicle steel convoys are quietly rolling down Chinese highways every single day, turning empty. Wind-blasted gravel plains into the highest-yielding power plants on Earth. By the end of 2025, the sheer volume of clean energy flowing out of regions like Xinjiang and Inner Mongolia had bypassed the generation capacity of entire industrialized nations, and the scale is only accelerating. The crane we watched fight the wind is already being supplemented by newer iterations, machines designed to push past the 190-meter threshold, built to handle even massive 8 and 10 megawatt onshore turbines that haven't even left the design phase yet. It is an infrastructure arms race where the prize isn't just energy independence. It is the absolute dominance of the next century's industrial supply chain, because the country that masters the art of building the largest, cheapest, and most efficient power generation network will inevitably dictate the cost of manufacturing everything else, from electric vehicles to advanced microchips. So, where does that leave everyone else? It leaves the global technology market facing a fascinating, deeply ironic truth. For decades, Western engineering was defined by its ability to create highly complex, microscale innovations, the silicon wafers, the software algorithms, the invisible code that drives the modern digital world. We grew accustomed to thinking that the future of human advancement would always be smaller, lighter, and more virtual. But the ZAT-8000H stands as a massive 4,000-ton reminder that the physical world still demands physical solutions. You cannot code a 150-ton power generator into the sky. You cannot write an algorithm to stabilize a 108-meter fiberglass wing against a thermal updraft in a barren desert. At some point, the digital world has to interface with the raw, heavy weight of reality. And right now, the machines doing that heavy lifting are rolling out of factories in places most people have never heard of, heading toward landscapes most people will never see, to build an empire of spinning metal that will shape the lives of generations to come. The true story of the world's largest wheeled crane is not that it broke a world record, or that it successfully completed a single impossible lift in the pre-dawn quiet of the Gobi Desert. The true story is that in an era completely obsessed with the invisible and the virtual, the most consequential transformation of our global energy landscape is currently being driven by something you can clearly see from miles away. A monster on 10 axles, reaching higher than the clouds, quietly rewriting the rules of the future by simply refusing to tip over. The next time you look up at a construction site in your own city and see a crane poking above the skyline, remember that you are looking at an old boundary. Thousands of kilometers away, out in